Next reaction we're looking at is when alcohol is converted to your halogenoalkane. Let's take a look at how this could be done. In the case of chlorination, you can use reagents like corn sulfuric acid and NaCl. In the process, in this reaction of corn sulfuric acid and NaCl, they will react and produce HCl gas. The HCl produced will then be able to react with alcohol to produce your chloroalkane. The next method is to use HCl gas. If you were to use HCl gas, you will need the presence of zinc chloride as a catalyst, and the same reactions will also take place. Alternatively, you can make use of PCl5. In the case of PCl5, you will find that you're able to react with alcohol, also similarly to produce your chloroalkane and as well as HCl. We'd like to highlight that as far as PCl5 is concerned, it's highly reactive because it's surrounded by 5 chlorine with large electron cloud. With 5 chlorine atoms with large electron cloud, hence a high strain energy, and that explains why it's highly reactive. During this nucleophilic substitution, what happens is that 2 of the chlorine will actually depart. 2 of the chlorine will be replaced with a smaller oxygen atom. That is actually from alcohol, and that's how you get a POCl3. And the 2 chlorine that has been removed, one of it will goes to the alkyl group of your alcohol to form your halogenoalkane, while the other one will actually go bind with the hydrogen from the hydroxyl group to form your HCl. In the same way, this is how SOCl2 or your thionyl chloride reacts with your alcohol. Again, for SOCl2, the shape is trigonal pyramidal. Again, the electron cloud of your chlorine is large and hence a high strain energy. In the chemical reactions, they will replace 2 of the oxygen. They will replace the 2 oxygen with actually the oxygen, an oxygen, and that oxygen actually comes from, and that oxygen is from the hydroxyl group of the alcohol. So similarly, the 2Cl, one of it will form your halogenoalkane, while the other one will form your HCl. And that's the reason why the byproduct is SO2. For both PCl5 and SOCl2 that's been used in this reaction as a reagent, we need to ensure that they are actually anhydrous, because both of them will hydrolyze and break down to form another compound in the presence of water, bromination. To replace the OH group with bromine, we could use corn sulfuric acid, again reacting with NABr, and this is the chemical reaction that takes place. So you will produce actually your HBr, and the HBr will then be able to react with your alcohol to actually produce your bromoalkane in this case, plus actually your water molecules. Otherwise, they could use PBr3. PBr3 could be produced by reacting red phosphorus and bromine, and obviously heating it. And in this reaction, they will produce the PBr2 in situ, and the PBr2 that's produced will then react with your ethanol. Take note that the equations are quite different from the earlier example that we covered, as the byproduct that's produced is your H3PO3, but the byproduct produced is your H3PO3, and bromoalkane is produced. Do note that in the chlorination, we could also use anhydrous PCl3, and the reactions is actually the same as that of using PBr3. Iodination. In iodination, we could only use red phosphorus reacting with iodine to produce Pi3 in situ, because Pi3 is just too unstable, and therefore need to be produced in situ such that it can actually react with your alcohol. And the reactions and the products of these 2 reactions are actually fairly similar as well.